Alright, so for this video we're going to start off by looking at several examples of series using the integral test or limit comparison test to find if they converge or not, and then we'll move on to some other tests. So we'll begin with this one, the sum n equals 0 to infinity of 3 over n plus 2. Now, this particular series, we can actually use either the limit comparison or the integral test. So for the integral test, we'll be looking at the integral from 1 to infinity of 3 over x plus 2 dx. So that is the limit as t goes to infinity. We'll see, I'll bring the 3 out. Then the integral from 1 to t of 1 over x plus 2 dx. Okay, now I could, well, I guess technically should do some u substitution here. If I let u equal x plus 2, du is dx, and so this becomes the limit as t goes to infinity of the integral. Let's see, when x is 1, u is 3, so if I want to switch my limits of integration, I'll be going from 3 to t plus 2 of 1 over u du, and so that is the limit as t goes to infinity of the natural log of the absolute value of u from 3 to t plus 2, which is the limit as t goes to infinity of the natural log of t plus 2 minus the natural log of 3, and that will go on infinity. So we show that the series diverges. Okay, so the integral test we were able to use here. It wasn't too hard to integrate this function. Now the other thing we could have done, alright, if I look at this, so I have a constant over n to the first power. Alright, if I want to use the limit comparison, alright, the series that I might want to compare this to is the harmonic series, alright, 1 over n, which I know diverges, and so the limit comparison test says I take the limit as n goes to infinity of, well, I'll use 3 over n plus 2 here, divided by 1 over n, and now that is equal to the limit as n goes to infinity of 3 over n plus 2 times n over 1, which is the limit as n goes to infinity of 3n over n plus 2, which is 3. So the limit comparison test says if the limit as n goes to infinity, the ratio between the two terms of two series is a constant, then the two series converge or diverge together. Since we know the harmonic series diverges, we know that the series, the sum of 3 over n plus 2 diverges as well. Our next example was, the sum n equals 0 to infinity of 3 over n squared plus 2. Alright, now for this one, okay, we could try to use the integral test. Alright, now that would mean finding the integral from 1 to infinity of 3 over x squared plus 2 dx. Now if you remember your Calc 2 class, alright, to anti-differentiate 3 over x squared plus 2, alright, this is a trig substitution that is going to involve arctangent, and so well, we don't want to go there. Rather, it's a whole lot easier to use the limit comparison test. Now what do we compare it to here? Well, a constant over n squared plus 2. This is a lot like 1 over n squared. So we will compare it to the sum of 1 over n squared, which we know converges. So if we take the limit as n goes to infinity of 3 over n squared plus 2 divided by 1 over n squared, alright, that is equal to the limit as n goes to infinity of 3 over n squared plus 2 times n squared over 1, which is the limit as n goes to infinity of 3n squared over n squared plus 2, which is 3. So in this case, once again, we get a constant limit between the ratios between the terms of the two series, which means the two series either converge or diverge together. Since we know 1 over n squared converges, we now know that 3 over n squared plus 2 also converges. Okay, so as you see, knowing about these p-series diverging and converging when they do one or the other can really help us with lots of series, if really any series where the top and the bottom are both polynomials of n. So we've seen a few examples here. If we look over at our next example, the sum n equals 0 to infinity of n over n plus 2. Alright, well here we don't have to use the limit comparison test. All we have to do is notice that as n goes to infinity, the terms of this series go to 1, which is not 0, and so the series has to diverge. Now here we have, for our next example, something a little bit more complicated. Alright, just to think about this, alright, so we said that 1 over n diverges, 1 over n squared converges. Well, what if instead of taking n and raise it to a higher power, we multiply it by, well, we could do natural log of n, but this is 1 plus natural log of n. So we're multiplying the bottom by something that goes to infinity, which makes the whole thing goes to 0 more quickly. Alright, so the question is it quick enough? Will multiplying by this 1 plus natural log of n on the bottom make the terms go to 0 fast enough that the whole series will converge? So here we could look at sum n equals 1 to infinity of 1 times 1 over n times 1 plus the natural log of n. Alright, I'm going to try to use the integral test here. I don't know what I would compare it to because I don't have anything with n log n's on the bottom that I know about converging or diverging. So I take 1 over x times 1 plus the natural log of x dx. Well, to integrate this, I'm going to do a u substitution. So I'm going to let u equal 1 plus the natural log of x. Now du is 1 over x dx. And so I have the limit as t goes to infinity of the integral from 1 to t. Oh wait, I need to change this. So if I want to change my limits, well, I can leave it as 1 to t, but I want to denote that this is x. Alright, let's clean this up some. So down here I have x equal 1 to x equal t of 1 over u du. And so this is the limit as t goes to infinity of the natural log of the absolute value of u from x equal 1 to x equal t. Now to get that back in terms of x, I'm taking the limit as t goes to infinity of the natural log of the absolute value of 1 plus the natural log of x from 1 to t, which is the limit as t goes to infinity of the natural log of 1 plus the natural log of t minus the natural log of 1 plus the natural log of 1. And what is that? Well, let's see. As t goes to infinity, the natural log of t will go to infinity. So this is 1 plus something going to infinity, and the natural log of something going to infinity is going to be infinity. So this is infinity, actually minus 0, because the natural log of 1 is 0. 1 plus 0 gives the natural log of 1, which is 0. Regardless, we have shown here, using the integral test, that this series still diverges. Okay, multiplying the bottom by 1 plus a log is not enough to make the series converge. So we've seen two examples here. One where the limit comparison test was pretty easy, but the integral test was difficult. And here's one where we didn't really know anything to compare it to. At least I didn't know anything obvious to compare the series to. But we could integrate. Now what about this next one? Well, that's pretty easy if we think about it. 1 over n times n plus 1, well, that's 1 over n squared plus n. We can compare that to 1 over n squared, and we will get the limit as a constant, so this one will converge.